All right, so we are now doing diffusion and osmosis lab. This is going to be a 2-day lab for either A cohort as well as the B cohort. So you guys are going to be kind of letting this sit overnight once we set up our couple parts. The first part's going to be a demo where you guys are looking at stuff qualitatively. The next part is more quantitative, so you guys will be collecting more numbers on that. I've numbered my pages. You guys have them on a Google Doc, so they'll pretty much go right in order, but just so you guys know where we are. You guys should have already been able to read through the introductions. That kind of covers page 1 and 2. On page 2, you guys are going to see exercise A. It talks a little bit about the procedure, which I'm going to run through each of these for you guys, and then we'll come back in that second video tomorrow and look at our results on them. So if we're looking at that first part, we're going to be utilizing something called dialysis tubing, and this is something you guys may have seen in first year bio. It's very similar to a selectively permeable membrane, so it almost looks like a little sandwich baggie. I placed it in water to make it a little more pliable. I've already tied off one end of it, so now it is kind of like a baggie. Into this little dialysis tubing, let's go back to it. I can buy this in different kind of concentrations, meaning I can buy dialysis tubing that has larger openings or smaller openings, kind of like selectively permeable cell membrane, so it allows certain things to pass back and forth through it. And that's what we're going to look at, what can move back and forth across this particular membrane. You want to make sure that it stays wet, and you want to make sure that you open it up all the way, which is why it's in water. And to that, I've already kind of made this little mixture of water, cornstarch, and glucose. So we have our large polysaccharides, cornstarch. We have our smaller polysaccharides, which is my glucose, and a little bit of water in there. And to that, I'm going to insert it into the baggie. So I'm making this solution of just kind of this water, cornstarch, and glucose. I'm going to put about 15 mLs, give or take, just so you guys can see it's kind of this white, creamy white color in there. This looks like a flour water mixture. Put a few more for you. And what we're going to be looking at is to see how things are able to move. So if you remember from our organic chemistry section, we talked about an indicator for larger polysaccharides. We said Benedict solution would test for sugars. We're actually going to use more of a test strip today, so we don't have to pour Benedict solution in it. But we also said iodine would be your indicator for starch, and we said that when iodine comes in contact with starch, you guys remember, it changes from kind of an orangey brown color to more of a purple color. So to the other end, I want to make sure I tie that end up tight, so both ends will be tied up. I want to give myself a little room within that baggie in case things are moving in case things are moving out. So I'm going to give it one more little tie. And I leave that like that for a second. And we're going to be putting it into a solution of water and Lugol's iodine. So this Lugol's iodine, once again, is going to test for cornstarch, so it will allow us to know if things are moving. So we change our solution to kind of this orangey brown color, just so you guys can see. There's the color through it. Oh, diffusion. Iodine's moving through the water. It's going to reach equilibrium, so it's evenly distributed throughout, kind of like what we did the color dye solution within the classroom as a demo. So before we do that, let's look at our chart on page 3. It's asking you guys some questions on this. So it's saying, okay, our bag, which we filled up here, it says the initial bag has 15% glucose, it has cornstarch, it also has water in there. It's asking you for solution color. So my color, I'm going to call it white, you can call it cream, but we're going to say it's kind of white. We're only doing initial. We haven't done final yet. Initial, I'm already tested it. I'm telling you flat out, we're testing it with sugar with test strips. It is positive for sugar. Well, I just told you that there is glucose in it. That's your sugar. We're not doing final yet because we want to know, does glucose move? Is it going to be in the iodine? Is it still within the baggie? In my beaker, we just put in there water and IKI. This IKI that you see here is iodine. That is my indicator for my polysaccharide, which is cornstarch in this case. So my solution color in my beaker, we can say, is kind of like an amber color, kind of like an orangey brown color that you guys see in there. And I know that within there is no sugar within there. I only put iodine, I only put water, so it's negative for sugar. We can do my little test strip, pull it out, there's no sugar in it. That's my initial. We're gonna let this sit until the end of this particular video, but what I'm gonna do is I'm gonna take my little baggie, I'm gonna place that in there. I want you guys to think, which way are things gonna move? Think about the eggs that we did. Is cornstarch moving out? Is glucose moving out? Is iodine moving in? Is water moving in? Is water moving out? What processes are they occurring in? So this is one of these kind of, hey, let's let this sit here and we'll come back to it at the end. So we're going to scoot over to the next one, which is exercise 1B. This is going through osmosis, or movement of water. So I have already gone through and made up a bunch of solutions, and you guys will see these on tables when you're in class, but we have distilled water, and we talked about distilled water before. It is 100% water. It has no solutes in it. So it is completely just plain old water. Then I started making sugar solutions. So the next table is going to have 0.2 molarity sucrose, sugar solution, 0.4, 0.6, 0.8, 1.0. So by the time we get down to the 6th container, super, super sugary sweet. To this, we're going to be filling up dialysis tubings, just like what we saw there. So we're going to show you the first one. We've already made up the other 5, and we're going to show you what we're going to do with them. But we'll do the distilled water together, and then we're going to be weighing them because we need an initial mass. This is where I said we're collecting quantitative data. So we'll go through the scales and we'll show you how to do that as well. So we're going to slide to our next table. You guys can see our tubes are already made up for 0.2, 0.4, 0.6, 0.8, and 1.0. I'm going to show you that we're going to do one right now with just plain old distilled water. So inside our dialysis tubings, we have 15 mLs of each of our solutions. So one for each solution. Distilled water, 0.2, 0.4, 0.6, 0.8, and 1.0. So you want to make sure that this is open all the way down. If not, plop it back in the water if it starts to dry out, because we want to make sure that we get all of this solution in here. This is probably the hardest part of the whole lab, is making sure that that pours in there. And you guys should have a little bit of an easier time with it because you'll have a partner in class to kind of help you, hopefully. And we're going to pour that 15 mLs in there slowly into my little baggie. And then I'm going to tie it off again. If you lose a little bit here and there, that's okay. We are going to weigh these anyway. So we'll have an initial mass, and then we're going to come back and weigh them next time as a final mass. You want to leave yourself a little room. Grab a string, tie it up so that way both ends are tied. You don't want to make it a super fit right where the water is because we're expecting movement. We don't know if things are moving in or out. But if things are moving in and I don't give enough room or space for it to move in, then we're not going to have accurate data. So you can blot them kind of dry if you like. If you think you got anything along the sides, it now is contained. So when I said this is kind of selectively permeable, it's not like we're going to squeeze it and things are able to go through the pores. That's how tiny they actually are. So this is my distilled water, and I placed them in front of each of them. We now need to weigh them. And once we're done weighing them and writing them down in our chart that you guys will see on page 6, you have a nice big chart, looks like this. We're going to go through and put them into cups of distilled water. So all my cups are the same. My only variable here is what's inside the dialysis tubing. So the first cup, I have a tube of distilled water going in distilled water. That should be an easy one for you. What should happen to it? Next, into distilled water, I have 0.2 molarity. Which way are things moving? 0.4 into distilled water, 0.6, 0.8, 1.0. All of them are going into distilled water. So as we're looking at this, you guys are using gram scales. It is zeroed right now. So you can see all of our numbers. We have 0 to 10 grams, we go by 100 grams, we go by 10 grams. So hopefully you guys are used to utilizing gram scales. The first thing and probably another hard part that you guys are gonna have, we're using weigh boats. So I need to kind of find the mass or zero out my little weigh boat. So this large weigh boat, I'm gonna go through until I hit that 0 mark again. And we'll say, very picky here. Say 5.6 is that weigh boat. So off to the side on my paper, I'm going to put weigh boat 5.6 grams. That means whatever the mass of my bag is, I need to subtract out 5.6. So here we go. My first one, which is distilled water, I'm looking for my initial mass. Putting it into the weigh boat, going through. I'm going to start off with a 10, see if that's too much. Nope, let's go 20, too much. So we'll say, okay, we're on 10. And we're going to go with 19.1. So it is 19.1 is my initial mass, except I need to subtract out my weigh boat. You guys are doing that part. That will give me my initial mass. That is going to go into my distilled water. It's going to go into this cup of distilled water. I'm going to put my gallon jug right behind it so I know what I'm dealing with. You kind of want to make sure that they're all submerged under there. It's okay if the top of that bag sticks out a little bit, but the liquid itself is submerged under there. Next, I'm going to go to 0.2. So these I've made up earlier for you inside my dialysis tubing. We've stuck 15 mLs of 0.2 within there. I'm going to put that on my next one there. I'm going to reset my scale. I kind of want to make sure that I'm still at about the same location, because as I'm going through and utilizing this weigh boat, maybe a little bit of sugar gets stuck into it. I want to make sure my results don't change. Yep, we're good. So we're putting it in there. So you're going, oh, well, it should be about the same. Well, it should be, but maybe I spilled a little bit along the way. Maybe the sugar adds a little bit more to it. So we can't just assume all these bags are going to be the same. Some of the bags are cut a little longer. Some are a little shorter. That part was not exact. So I can't really say the bag length is a constant there. So let's go 19.2 on that one. So we're going to say 19.2 grams minus 5.6 grams for my weigh boat will give you guys your initial mass for the 0.2 molarity of my sucrose. It's going into my second cup of distilled water. That's the solution that's in the baggie. Go through, sure. And I'm going to grab my next one. .4. Going through. Check and see what we have. Should still be about the 19 range, we're hoping. So this one's going to be a little heavier on you guys. So I'm going to go 19.8. Still weighing out 5.6 grams for my weigh boat. Sticking that into my third cup here of distilled water. And we're going to go up to my 0.6. So my solutions are getting a little more sticky along the way. You can hear my shoes actually sticking to the floor where we spilled some along the woman. I reset my weigh boat. We're still at 5.6. Let's check this one out. We're on 0.6 molarity. Might have to bump this one up a little bit. So we're going to go all the way back. We're going to increase this to 20. Remember, my sugar solution is getting a little bit more concentrated as we go along here. So we're right now on 20. It's just barely over 20. So we're going to say 20.2. We're still subtracting out the 5.6 grams for my weigh boat, and that will give you your initial mass. Once again, it's going into my cup of distilled water. All my red cups hold distilled water. The variable here is what's inside the bag. It's different concentrations of your sucrose. We're up to 0.8. I'm going to reset just to make sure. Okay, so we figure about 20. So let's go over to my 20 mark. That's where we were last time. Let's go 21.8. We are at 21.8 grams. Still subtracting out my 5.6 grams. Will give you your initial mass. This is now going into cup number 5. Still distilled water, but inside the tube or the dialysis tubing is your 0.8. Now, if you're looking at your concentration colors, they're getting like more and more cloudy looking. It's because it's got a ton of sucrose as opposed to distilled water. You absolutely can tell the difference between those two solutions. So we're up to our 1.0 molarity. I'm gonna go back, just double check one last time, make sure that my scale has been zeroed. Good, going in there, go back, we're gonna go back to 20, probably about 20, a little bit less. So either this bag's a little shorter, got a little less in it, which is fine. We're still going by our masses here. Let's go 20 points. Let's go 20.5. So my initial with the weigh boat is 20.5 grams. We need to subtract out my 5.6 for my weigh boat. That will give you that. We're gonna stick this in my last cup. They're gonna sit. If you're in class, it's gonna sit actually 2 days until the next A group comes back in. If you are online virtual, you're gonna have to wait another day, or a day or two. We're actually gonna film this tomorrow, so we're gonna let them sit for about 24 hours. Once that happens, we're gonna find our final mass the same way we just did initial mass. Then you want to look for your percent change in mass. That's the formula you guys are going to be using. So final mass minus your initial mass divided by initial mass, you're going to times it by 100. That's going to give you your percent change. You guys will be graphing that. We'll talk about that more once we collect that data. So that's the second part of our lab. You guys can graph there. It's going to talk about a little bit of the questions as you go through. Now, we're going to look at water potential. We talked a little bit about water potential with your osmosis notes. So there's a little bit of reading here for you guys with some symbols. It talks about water potential. And we are now up to the next particular part. So we're working with potatoes. We're shooting to the next table. And as we go through potatoes, you're going to notice new cups. So these cups now do not have distilled water. They have the solutions that you see in front of them. So we start distilled on the far end, 0.2, 0.4, 0.6, 0.8, 1.0. And what we're going to end up doing is we are going to cut pieces of potato. So in order to do this, we have all of our potatoes. You guys want to get a 3-centimeter plug of potato. So we want to make them uniform. And in order to do that, we're going to use a potato core. So this is my little potato core. It's very sharp on the ends. We're going to take it and we are going to go, hopefully, straight down with it. A little cut into it. Straight down, twist, pull out. There's my little core of potatoes. Bring it out. Just get the excess off. So my skin I don't want because we weren't going to diffuse across that much. So I'm going to take a knife, I'm going to cut straight down on that. And I want a 3-centimeter plug. I'm going to hook it up to my ruler. There's 3 centimeters. We need a whole bunch of these. These we did not make early for you guys because I didn't want them drying out too much. So give me a second. We need 6 potato plugs. They should pretty much be the same. They're all the same brand of potato, the same species, the same size plug. Cutting off the skin off of one. We're going to make them all 3 centimeters. If they're not exactly 3 centimeters, we'll be like, okay. We're still grabbing our initial mass. Let's see if I can get another one out of this. That's going to give us what we need. So we'll jump on to the next one. So we need 6 potato plugs, 1 for each of our solutions that we have. acid. We're just going to go with a fresh potato. All right, so now we got to go through, cut our edges off, no skin whatsoever on them. You're going through, we're measuring our 3 centimeters. Make sure everything's nice and straight on your cuts the best you can. And what we're going to be looking at as we put these into our cups of solution, we kind of want to find what or where is this potato going to reach equilibrium. Somewhere along the line, it should not gain mass and it should not lose mass. So once again, we are back on the scale. We are back on chart. So if you guys look at page 10, it says table 1-3, group data. Group data is going to be a little hard. You guys will get a little group data from me. You guys are going to get a little group data from some other groups. I'm just going to use color scale. And hopefully we'll get some good data along the way. So I'm just going to pull my scale over that we just used because I know that it's in great working shape. The same weigh boat. So I'm going to go through. Let's make sure we're still at 5.6. Should make life a little easier for you guys. Okay, so now weigh boat is still 5.6 grams. You still need to subtract it out from the potato. Okay, temperature, hang on to. We will come back to that. I will give you temperature when we do our final there. Potatoes going in. Yes, I need to weigh every one of them. So we're going through. So let's say our first one. Let's go with 15.7, so it doesn't really matter. Let's say first one will go to distilled water, that's where it will be going into. It was 15.7 grams minus our 5.6 grams weigh boat will give you your initial mass. It's going out, I'm sticking it into my cup that says distilled water, which is what's inside that cup. Now my only variable is what's inside the cup. Unlike the second part where we did, the bag was different. My potatoes should all be the same. It's important to get an initial mass on each of these. So if you're in class doing it, you guys would not be doing 6 potatoes like I'm doing here. You guys would not be doing 6 baggies. You would be a part of a group, so you would be doing one section. You would be either doing distilled or 0.2 or 0.4, and that's where we're collecting that group data. So where these potatoes should kind of all weigh the same, we're going to be a little different on you. So where they're all from the same bag, maybe they all weren't from the same potato. But as long as we have our initial mass, we're okay. Let's go 15.1. It's 0.2 sucrose. We're going to go 15.1 grams. We got to subtract out our 5.6 grams for weigh boat. That will give you your initial mass. This one is going to go right into my 0.2 molarity water. Going back, we're doing it again. So I want to recheck that weigh boat each time because you're going to notice there's a little bit of potato juice that's left in there. Not enough to change my mass yet, which is good. Next one's in. Go through here. This one looks a little heavier, which is fine. We're still going by our percent change. Let's go 15.9. We're going to subtract out that 5.6 grams. This one's going into my 0.4 molarity sucrose. A couple more, going back to 5.6 just to make sure my weigh boat is even. My mass for my 0.6 molarity. Going to be, let's go 15.6 minus your 5.6. That's going into cup number 4, 0.6 molarity of sugar. My fifth potatoes, which is going to go in the 0.8. A little heavier. So we're now going to go 15.8. Subtract out that weigh boat, still at 5.6 grams. Here we're going to go in 0.8 molarity. My last potato going in the super sugary solution. Weigh boat is still good. Pop it in. Lighten it up a little bit. We're at 15.3 minus our 5.6 grams. That will give you your initial mass. This one is going into that really sugary sweet solution. So think about it. Water's moving. Where do I have more solute? Where do I have less solute? Think about the potato. Potato's got a lot of solute. It's got a lot of starch and stuff in it. My solutions. Which way will water move? Which of my potatoes is going to gain mass? Which of my potatoes is going to lose mass? Which will become turgid, which will wilt. And we'll actually be able to see some of that as we go through it. Somewhere along the middle here, you're going to find a spot where that potato reaches equilibrium, and that's going to give you the molarity concentration of that particular potato. How much solute does it have? We can find it out by looking at sugar solutions. What that means is that it will not gain or lose mass. It may not be exactly 0.4 or 0.6. You guys will be graphing it, and wherever that graph hits the 0 mark, it may be like 0.32 molarity, but you'll be able to determine it based on the graph that you have. So we'll come back, we'll do our final mass, which will give us the same formula for percent change in mass. There will be a little extra credit, and we'll talk about, so we'll just move our data here for everybody. So this will be your final data when we get there tomorrow. You guys are going to go through, create your own graph. I'm going to give you an example of what it looks like, because we're going to have a positive change in mass, we're going to have a negative change in mass. So wherever that line crosses 0 is going to be your molarity of sucrose. It's going to be your molarity of that particular potato, which is what we're going to be putting here. There's one extra credit question here for you guys. It deals with water potential. This little starred area is my extra credit question. Questions 4 and 5 are not extra credit. Questions 4 and question 5 are a must-do question that are dealing with that particular part. But extra credit, it deals with water potential. You guys can go through, and that's why you're going to need the temperature of it, and we'll come back to that. So we kind of want to backtrack just a little bit, and we want to go back to our first little observation that we were doing. So let's go back to our first one. That was table 1.1 on page 3. I said, hey, let's let it sit. We'll look at it, we'll come back to it and see what's going on. So if you remember, we started out, the baggie had glucose, the baggie had starch in it. The water was iodine as well as just plain water in it. Baggie started out white. Now what we have, I'm going to blot this off just so you guys can see. That's my baggie now. It's kind of this gross purple black color. So what does that mean? Well, we just said iodine is a starch indicator, and when iodine and starch come in contact, that iodine turns basically a dark black or purple. So I can say that iodine is moving into the bag. So you think, well, does cornstarch move out of the bag? Well, the answer is going to be no, and the reason I know that is that solution is still kind of an amber black color. It's not a purple color, it's still the same color we turned out to be. If that white cornstarch moved out, my solution here is going to be black as well, like what we have inside the bag. So why doesn't cornstarch move? Cornstarch is huge. It is a very large polysaccharide. So when we say, okay, well, which way does things move? My final color, we can say for the bag, it's going to be kind of this black purple color. And you guys can see that there. My beaker, still the same color we started out with. It is an amber color. So maybe some water moved out, but definitely no cornstarch. We tested with test strips, and we're going to test for sugar. So inside the bag, I still have sugar inside the bag. It's still positive in there. My sugar, my glucose, I'm going to say it's negative here. It did not move out. So even though we think of sugar as this tiny little molecule, it's still too large to fit through that particular molecule. So if this had been our cell membrane, it may need help with maybe facilitated diffusion. Maybe it needs helper molecules to move through. If this was a cell membrane, that glucose in this example would not be able to go through that phospholipid bilayer. Iodine absolutely did. Absolutely moved through into there, and we could tell by this color change. So you guys are utilizing that information from table 1.1, and you're answering 3 questions that you'll see here based on it. So this is all qualitative, color changes, information you see, nothing to deal with numbers. The rest of it, part 2, which is our dialysis tubing and distilled water, and part 3 are potatoes in different solutions of water. We will come back to you tomorrow. They kind of have to sit. We'll get final masses then and talk about our data results.